In today's lecture, we will study about the arc lengths. So we already have studied about the length of the line from the point, any point to any other point. So in the previous literature, we were calling it as a straight line segment, and we could have computed without using the calculus concept, like the final point minus to the initial point. We can have the length of the curve, or to the line. Now, by using the concept of the calculus, we have to find the length of the curve, which is the y is equal to f of x. For instance, if we have these axes, this x comma y, x and y, and there is a curve, this one, and this is established by the function f of x, and this is starting from the point A, and the final point, we shall say that this point is B. So we have to compute the length, uh, or you can say the arc length of this curve. So of course here the A and B are discretized, finitely discretized, and this x does belongs to A comma B of the closed interval. So for this, I would like to copy a figure from the book, which is this. In this case, we can say that the curve whose length we want to find is the graph of the function. So this blue line is this one, is basically the function of f of x from point A, which is this one, to the final point B. In order to derive an integral formula for the length of the curve, we assume that the function f, which is the represented by the blue curve, is continuous, and a derivative exists at every point within the interval a comma b. Of course, this is defined on the interval a comma b. So one can say that the derivative exists on each point of the curve, because since the function or the curve is smooth, and the graph is smooth curve because it does not have any breaks or corners or the curves. You see that from this point to this point, the graph is completely smooth. If we have to look at this moment, we have to look the blue line, and this is the graph of the function f of x, and this is completely smooth. We can also call it as a smooth curve. Now, like we did before in the previous lectures when we were finding the volume of the solids, since from A to B, these are the initial and the final points. So if I say that A is the initial point, let me say which is the x naught. So and the forthcoming point is must be x1. So of course x1 is larger than or equal to the x naught, and similarly x2 is larger than equal to the x1, and similarly x3 is larger than equal to the x2, and similarly this practice goes on up to the x n minus 1 and larger than equal to x n, and this is equal to b. This is equal to b. So all the points x naught, x1, x2, 3, xn minus 1, xn, they are lying within the interval a comma b, is this within this interval. Now if this curve y is equal to f of x is evaluated on a single point, let's say any point I could call that one can evaluate, let's say at this point p of k. So this is called yk is equal to the function is evaluated on the point x of k. Then the corresponding point, of course, if this is the point here, the value of x comma y would be xk comma yk, and this point would be called to the pk. Of course, this is lying on the curve. As the values of k increases or decreases, this will move along the curve. Either this will move towards the final point B, or this will move back to the final initial point A. So if we look the segment of this one, this is the xk and this is the xk minus 1. So in that case, we can have the width of the interval. The width of the interval can easily computed by, like we have done in the previous lectures. This is easily computed by delta xk, which is xk, which is this one, minus xk minus 1, and this is called the width of the interval. We can say that this is the delta xk. As the value of xk increases, this can be go forward or to the backward. And similarly, this is only for the x. In order to compute the width of the y, for this I will cut this piece into another part, this piece, basically this one. So I can write it as here like this. This is the x, this is the y. So basically I am copying this piece over here into the larger segment. So this point is basically xk minus 1, and the final point is xk. And the curve is plotting on this point is something like, with the blue one, is this. Maybe I can move it a bit curved. Like this, okay? And if I try to attach by some points, this is the xk minus 1 and this is the xk. Of course, we have already computed the distance between them, and this was the delta xk from, and the corresponding point is this one. This point is xk comma yk, and this point is xk minus 1 comma yk minus 1. So we have computed the distance from here to, from xk minus 1 to the xk. Now in order to compute the distance for the y, of course the y is starting from here to here. So this is the point yk. Of course this point is yk from here to here. For this you can also have the straight line segment from here to here, and of course this distance is this one. Is this basically, this is the maybe I can write delta yk. Of course xk yk minus yk minus 1. So this is the distance of the y, and this is the distance for the x. All together we have both computed delta xk and to the delta yk. And the one more crucial thing in this, we can I just took this segment into the larger picture, is this one. So I just took the one segment of this arc length or the curve, and I treat this segment separately, just for your better understanding how we can compute the delta x and delta y. And in order to compute the straight distance between them, you can have the delta yk, and you just draw a straight line. You directly have the points. You can also compute it by the final point minus to the initial point. So we can write here explicitly as we already have done by the delta xk, which is xk minus x1. Now for the delta yk, from here to here, basically delta yk is yk minus 1. Now if you want to compute the distance from this point to this point, we can use the notation like lk, because for the moment we are just computing the distance from the one segment, is this one. So lk by the usual formulation, which is the delta xk squared the distance formula plus delta yk whole squared. So of course it's the xk minus 1 plus yk minus 1. But our point is we don't need to compute only the distance of the or the length of the one segment. We have to compute the length of the all the segment from here from here to here, here, and all of them. So for this, I will sum up by the sum. Let's say the sum of k is starting from 1 to n lk, and this is the equivalent to the sum k is starting from 1 to n, sum of this delta xk squared plus delta yk squared. So this thing is basically the same. I just sum up of the all small segment for the different values of the k. Now we expect the approximation to improve as the partition between the interval AB become finer. So by the mean value theorem, we know that this delta y, we can write it here like delta y, the change in y divided by change in x, is basically the first derivative f dash of किसी any point of the f of ck. So of course, if this is evaluated on any point somewhere here c, this is the point f dash of ck. So we can say that delta y k divided by delta xk is equivalent to by the mean value theorem f of ck, and f of ck is the midpoint between the intervals ab. So one can write here by the mean value theorem, right? So from here I can just write it as delta yk is equal to, sorry, this was f dash of ck times delta xk. So we have basically computed the value of delta yk is this one. So this is our main equation. Let me call that this is the equation star. So we can substitute this delta yk into our equation star. Substitute in equation star, we find the sum k is from 1 to n lk. I'm basically writing this equation over here. The sum k starting from 1 to n delta xk squared plus f now at the place of delta yk I'm substituting this expression f dash of ck times delta xk whole squared, right? Now this is delta x squared, we can take the common from here and we can write it as over here as a sum of k starting from 1 to n sum. So I took the delta x k squared common from here, and once you take out from the square root, so this will become like 1 plus f dash of ck whole squared, and this is out of the square root. So this is the delta xk. Because we have to treat this expression. This is the continuous over the interval AB. One can say that this is the continuous because we already said that our curve was continuous. This was the smooth curve, and we already built the argument within this interval A to B. This is the smooth, and the all at every instant or every point the derivative exists because of the smoothness of the curve. So since the function is smooth, derivative exists. This is why we can say this is a continuous on the interval a comma b. Now we can use the limit of the Riemann sum of the right hand side of this equation. So in this case, as a norm of the partition goes to 0, so which is very simple, like we have done before in the previous cases when we're computing the volume of the solids. The limit n goes to infinity. Whenever n goes to infinity, delta x k goes to 0. This means that the distance between the two points, which is the one triangle, they are getting smaller and smaller. K is starting from 1 to infinity. Lk is equal to the limit is the same as this one. N goes to infinity. K is starting from 1 to n. 1 plus f dash of ck squared and to the delta xk. So basically this is the definition which is represented by the Riemann sum. Now we know that the Riemann sums and to the definite integral, they are equivalent. So we can say that this is from point A, the B, 1 plus f dash of x squared and to the dx. Of course, the width of the interval is converted into the differential, which is dx, and this comes out as it, and the a and b is coming from the length of the curve, which is because it was starting from here and ending up to this point B. And this is basically the formula for the arc length. So I will explain you here, like this is the formula or the expression of the arc length. So in this he's saying that if f prime is continuous on the interval AB, this is, we already built the argument the why the f dash is continuous, because the function was smooth and derivative will exist on each point, and this is why we are saying over here the f dash is continuous on the interval AB. Then the length or the arc length of the curve, which is of the function y is equal to f of x from point A to B, is the value of the integral, which is the same as we have written before, is this one. This let me call equation 1, and let me say this is equation 2. They're the same that we have built. Of course, f dash of x is the dy by dx, is the first derivative. By this formulation, we can compute the arc length. So I will just move to the question. Okay, this is the question. In this question, we have to find the length of the graph or the length of the curve. So let me represent this as a question. So find the length of the graph. The function is given like f of x is equal to x cubed by 12 plus 1 by x, and x is ranging between 1 and 4, and this is the closed interval. So first let us try to plot the graph, and the graph of this function looks like this. This one. So let me say that start from the solution. Solution is this one. So we just have plotted this function, which is the x cubed by 12 plus 1 by x, and the x is ranging between 1 and 2. Of course, this point is a comma f of a, and this point is b comma f of b. And we know that our a is small a is equal to 1 and our b is equal to 4. For the, now if you want to write the specific points, you can substitute the value of a in this function and you can have the value of f of a, and likewise for the function f of b. Now we see the trend of this blue curve. This is continuous over the interval a to b. So from since the interval is restricted from 1 to 4, of course it's a closed interval, between the interval a to b, we see that the trend of the graph is continuous, and that we don't find any edge, any curves, or any bumps in the graph, or any kind of discontinuity. So we from here we can easily compute the arc length from point A to the point B. So first we have to find the derivative. We have the function f of x. Of course, y is equal to f of x, the function, and our f of x is equal to x cubed by 12 plus 1 by x, right? And of course, x is ranging between 1 to 4, and its derivative does exist as a, so this is the x squared, and 3x squared divided by this, and this will become 4 minus, and this is the 1 over x squared. And of course here x is, this derivative does exist on the each point of the between the interval 1 and to the 4. Now the formula of the arc length was we already derived, which is represented by the equation number 2. So in this case, this is the formula. This we can write this formula as it over here. So the arc length L can be represented by A to B 1 plus f dash of x whole squared and to the dx. So we already computed the first derivative, which is this one, and let us first compute this, which is the 1 plus f dash of x and to the whole squared. So this will become 1 plus, this one is as it, and f dash is x squared by 4 minus 1 over x squared and of this whole squared, and this will equivalent to the 1 plus x4 by 16 minus 1 by 2 plus 1 over x4. And if you write the final form of this, we can have like x raised to power 4 divided by 16 plus 1 by 2. 1 minus 1 by 2 is plus 1 by 2 plus 1 over x raised to power 4. And also you can write it as by the completing squared, x squared by 16 plus 1 over x squared of the whole squared. So we know that x is ranging between the interval 1 comma 4. So by this formula, let me call the equation alpha. From equation alpha, we find L is from A to B. A is 1 because this is starting from 1 over here. 1 and ending up to the 4. This is 4. And the root of 1 plus f dash of x squared, this has come out x squared by 16 plus 1 over x squared of the whole squared. So this squared is cancelled by the square root. Of course, this is the dx. And this is equivalent to the 124 x squared by 4 plus 1 over x squared. And sorry, I did a mistake, and this will be equivalent to 4 but not 16. So we can write it here as a 4. And also this is a mistake. This is the 4. Sorry. Okay. Dx. Now you can easily solve this integral and you can have the answer by some manipulation, which is 6. So the length of the curve from A to the point B is 6. This is how we can compute the length of the curve by using the some calculus concepts. There is another question. In this question, we also have to find the arc length of this function, which is ranging from x is equal to 0 to x is equal to 2. So let us start the work. Solution says we have the y is equal to f of x. This is our function, right? And our function f of x is equal to x by 2, x by 2 power 2 by 3, and x is ranging between 0 to 2. So if we take its first derivative, which is the f dash of x, we have that 2 by 3 over here, x by 2, and this is the 2 by 3 minus 1 is a minus 1 upon 3, and the derivative of this is 1 by 2, and all together this goes away, and all together we will have 1 by 3 x by 2 and to the minus 1 by 3. And the graph of this function is basically, I can plot here, is this. This is the x and this is the y. This is basically start from, of course, from 0 to 2. So this is the graph of the function y is equal to x by 2 and to the 2 by 3, power of the 2 by 3. Now we have the limit of the x is ranging between 0 and 2, and we find that our f dash of x is equal to 1 by 3 x by 2 power 1 minus 1 upon 3, and x is ranging between 0 and 2. Now from here it is clearly seen that if you substitute x is equal to 0 in this function, so this means that this is a 0 by 2, which is of course if you invert them with this power minus 1 by 3, so this f dash is not defined at x is equal to 0. We can say that is not defined at x is equal to 0, because if you substitute 0 in this expression, because of this minus, this will reciprocate, and because of this will become 2 over 0, and 2 over 0 is infinity. This is why I have not defined this graph of the graph of the function over here, because at 0 this is undefined. And now we had the formula for the arc length was, which was length was equivalent to the a to b 1 plus f dash of x whole squared dx. Now we see that at our interval between 0 and 2, the derivative does not exist. So once the derivative does not exist, this means that we have the discontinuity or the any abrupt change, or you can say that the function is not defined at the one endpoint of the interval. So for the and at x is equal to 0, this is not defined. For this we will discuss its discontinuity at x is equal to 0. For this we will have the little modification, which is like this. In this we have to deal with the discontinuity of the dy by dx. Of course, this is the f dash is dy by dx. This is the first derivative, and we are facing the discontinuity at a point which is x is equal to 0. So in this case, we may able to find the curve length by expressing x as a function of y and applying the following analogy of the equation of this equation in the previous, which is defined like by the equation 3. Now we have the function in the start. Let me call this is the equation star. Of course, this is the y is equal to f of x. So in that case, we can say that y is equal to x by 2, which is the 2 by 3. Now in this definition, he is saying that the curve length by expressing x as a function of y. So we will solve this equation for x. So we can just take the some simplification, which is become 3 by 2 on the both sides. So x by 2 has come over here, and if you solve it for the x, so this is x is equal to 2y 3 by 2. And now rather than having y is equal to f of x, we have the x is equal to f of y. Now if you go back to this definition, which is represented by the equation number 4, now here we are saying that, or maybe you can call it g of y, right? If g dash is continuous on the interval CD, the length of the curve x is equal to g of y from point A to the point B is given by this formula. The only change appear over here, rather than computing the derivative with respect to x, we will compute the derivative with respect to y, provided that first we have to simplify the function in terms of x. So this is, we have solved it for the x. So x is equal to 2y power 3 by 2. Now in this case, if we want to take the derivative, which is the from here dx by dy, now you see we have having the derivative with respect to y. Now the first derivative of x is equal to 2y 3 by 2 is 2 as it, and the y at 3 by 2 minus 1 is 1 by 2, and this 3 by 2 is here, and all together this has become 3 into y 1 half. Now the limit of the integration, we have that which is 0 and 2. Now we have to solve this limit of integration rather than for the a to b, but for to the c to d. When we have, when x is equal to 0 in this case, then Let me call this is the equation beta. Then equation beta implies like x is equal to 0 over here. So this is a 2 into y 3 by 2, and this implies that y is equal to 0. This is the one limit of integration, which is c. We can also call that this is c. Maybe here like this. When x is equal to 2 is this one, or the other upper limit in terms of x, then equation beta implies like 2 into 2 times y 3 by 2, and 2 is 2 is, so this is the y is equal to 1. So we have this d. So we have found the limit of integration. So we just substitute our limit of integration, our derivative, which is 3y 1 by 2, into our equation number 4, and we find the length, arc length of the curve. Arc length of the curve where the original curve was discontinuous at x is equal to 0. So let's have a look. So in this case, length L is equal to c to d is now, this is c is 0, and the d is upper limit, which is 1, root of 1 plus dx by dy, which is the dx by dy is the 3y 1 by 2 whole squared, and this is equivalent to 0 to 1, 1 plus 2 and 2 cancel, and this is 9y, and to the root dy. Of course, dy will appear over here also. And when you solve this expression by integration, you will find that the answer would be 2.27. So the length of the curve from this point, basically it was initially 0 to 2, and this point was up to 2. This was the x, but we have transformed in terms of y from 1 to 2. So the arc length of this curve is 2.27. So this is how we have related the discontinuity by using the other method, or the other changing of the variable. We can find the arc length if we find the discontinuity at dy by dx. We can transform it to the dx by dy. I have chosen one question of the exercise 6.3, and this is the question number 13. And in this question he's saying that find the arc length. So we have only this expression, x is equal to 0 to y secant 4t minus 1 whole root dt, and the y is ranging between minus pi by 4 to the plus pi by 4. And we know that in order to compute the arc length, we have the formula like the length is given like, maybe I can write solution over here. Length is given like from, since it is in terms of x, so this is c to d, and this is the 1 plus f dash of, or g dash of y dy, and of course the y is ranging between minus pi by 4 to the plus pi by 4. So let me call this is the equation star. So differentiate equation star we find that dx by dy. So this will basically become like secant to power 4 y minus 1. Since this is in terms of t, so basically it was like 0 to y, and this is dt, and we have to differentiate with respect to dy. So here basically we have applied the first fundamental theorem we have already studied in the previous chapter. So altogether this will become in terms of, so sorry, this is t, secant square t. So since the upper limit is y, so this will become secant raised to power 4 y minus 1. So I can explicitly write it as that dx by dy is equal to the secant squared y minus 1, and the dx by dy whole squared is equal to secant raised to power 4. This was 4 minus 1, secant raised to power 4 minus 1. So of course the y is ranging minus pi by 4 to the plus pi by 4. So first let us take a look of this graph. So the graph of the function does look like this. And this one. So y x negative, and this is the y negative, and of course we have working for the y, so this is minus pi by 4, and this is the somewhere here, this is a plus pi by 4, and the x is given like from 0 to y secant raised to power 4 t minus 1, and this is the dt. So we have already transformed into our question form. So, and now we see that I will use this equation, let me call equation 1. By equation 1 we find that the length is of course from minus pi by 4 to the plus pi by 4. This is the 1 plus, of course, g dash of y. Of course, this was g dash of y whole squared. So this has come like secant raised to power 4y minus 1 whole squared because of this definition. The definition is from c to d square root of 1 plus g dash of y whole squared dy. And this is equivalent to minus pi by 4 to the plus pi by 4. Sorry, this squared will not come, this one. So if I write directly it as, so this minus 1 and this plus 1 goes away. So this is the secant raised to power 4 root y dy. And since the root is 1 by 2, the 1 by 2 is power cancel out. All together we will have like minus pi by 4 to the plus pi by 4. This is the secant squared something like secant 4 of y is something like 1 by 2 dy because of this square root property, and this is minus pi by 4 to the plus pi by 4, and this is the secant squared y dy, and we all know that the integration of the secant square y is the tangent y, so that this is equivalent to the tangent y minus pi by 4 to the plus pi by 4, and then this is the 1 minus 1 is equal to 2. So we find that the arc length from minus pi by 4 to the plus pi by 4 from here is the 2. So here the analogy of the question was a bit different, because the argument we have given was in terms of x. So we started by the differentiating this x with respect to y, and we already know that the arc length formula from c to d1 plus g dash of y whole square dy. So we found the first derivative with respect to y, and then we substitute into our expression of the arc length, and we find the arc length which is equivalent to 2. Similarly, I would recommend you to solve some question from the exercise. The questions are exercise 6.3 and the question number 1, 3, 5, 7, 10, 12, and these from 1 to 12, these question ranging are the previous are the same like we have done in the previous examples, like this one in the previous examples, like either in the terms of discontinuity or they are completely continuous, while the questions are from the 13 I have done, and you can also take a look on the question number 14. The question number 14 is on the pattern of the question number 13 that we have recently done. So you can take a look on this question. If you have any problem, we can discuss in the next tutorial.